As of this moment, there is virtually nothing that can compete with the Raynox DCR-150 as a tube lens for using with most of the common infinity-corrected microscope objectives we use in macro photography, especially when you consider the price. But is this new 5-diopter lens that we recently tested as a close-up lens going to give Raynox something to worry about? A few weeks back, we tested the 58mm NiSi Closeup Lens, and it performed quite well in that role. But what we're doing today is something completely different. I am going to take this lens and compare it head-to-head with the Raynox DCR-150 as a tube lens for use with an infinity-corrected microscope objective, and see if this lens can also compete in that area. I think that there are features of the NiSi that make it an easier to use and more durable close-up lens. So if this thing can also perform as a decent tube lens, there might be reason to consider switching from the old DCR. And that's the purpose of today's little test. We're going to compare these two head to head and see how they perform. This is Alan Wall's Photography. I am Alan, and you are welcome back. Thanks to all my Patreon supporters and the folks who support me through my website. Couldn't do this without you. Thank you very much. So what exactly is a tube lens? Well, back in the old days, microscopes usually used what's called a finite objective. That is a very fancy lens that takes the light from the subject and focused it on a plane right in front of the eyepiece. And we still use those objectives in photography. We'll place the objective at a specified distance from the sensor, and the light rays will focus on the sensor, and we can take our picture that way. But over time, and with the introduction of new technology, microscopists wanted to be able to place additional optical elements somewhere in that flow of light. Now, the problem was that these elements that they wanted to put between the objective and the eyepiece would themselves have an impact on the quality of the light getting back to the eyepiece. But in today's modern microscopes, the objectives, which are called infinity corrected, instead of focusing a beam onto the focus plane, they actually just output a flux of parallel light rays. Now, these rays of light will never converge. They're theoretically parallel forever. And that allows the microscopist to put these additional elements, be they beam splitters or dichroic mirrors or whatever they want to put in there, before the image is focused onto the sensor. So once the light has traveled in parallel through this infinity space, then the light rays, as parallel rays, hit the tube lens. And what the tube lens does is focus those beams just like the old finite objective used to, right onto the sensor or the eyepiece. So that's the difference between the two. In order to get the full rated magnification of an infinity corrected microscope objective, you need to use a tube lens, like the Raynox, of a fairly specific focal length. And most of the modern infinity corrected scopes use a focal length for the tube lens of 200 millimeters. There's one important point that's going to come up again soon, and that is you don't always have to use the rated focal length for your tube lens. For example, Raynox also makes a DCR-250, which has a much shorter focal length of only 125 millimeters. So you can use that lens with the same 10 times objective and get a very sharp image at 5 times magnification by shortening the focal length that much. So there is a little bit of flexibility in how you use your tube lens or the tube lens that you select if you're willing to accept fluctuations in the actual magnification you get from the system. Now, there are quite a few out there who believe that the quality of the tube lens is kind of secondary and that all of the magic happens in the objective. And up to a point, that is true. I mean, all of the aberration correction in modern objectives like this is done inside the objective. So the quality of this is paramount. But it is also possible to put a tube lens in line with this objective that could degrade the image. So for that reason, I think a tube lens needs to be of sufficient quality to serve its role as this intermediary or relay lens well. Now, there are several different solutions that photographers use when they need a tube lens. One is that you can take a microscope apart and remove the tube lens from it, and then you have a tube lens that's a tube lens. But dedicated microscope tube lenses can be pretty expensive. And we've come up with other alternatives that give equally good performance. And of course, the one we're testing against today is the Raynox DCR-150. A tube lens is a lens, and as a lens, it is prone to aberrations like any other lens. And that's why we're testing these two lenses today. So to do this test, I'm borrowing heavily from the technique that Robert O'Toole uses. He is something of a guru when it comes to relay lenses and microscope objectives. I'll put a link to his website in the show notes. If you haven't been by his website, you absolutely must. It is a fantastic resource. So the test itself is pretty straightforward. I set up a very standard bellows setup with an APS-C DSLR as my camera, a set of bellows, and attached to the front of the bellows, the relay lens. Now, I repeated the test with the lens facing forward and with the lens in reverse. Now, one thing that I held constant across all the tests was I used a 50 millimeter infinity space. So there was an additional 50 millimeters before you get to the objective. Now, in all of the tests, I used the Nikon CFI Plan 10 times infinity corrected microscope objective. It has a nice wide aperture. It's a great lens for photography, one of my favorites, and considerably more affordable than a comparable Mitutoyo. So that was the setup. So to test the lens, we needed a specimen. And I wanted something that was very flat, very regular, had lots and lots of straight lines in it, and a fair amount of contrast. So what I decided to use was a computer chip, a silicone wafer. And that was also that I could see any aberrations that were produced by the lens. So you may well be wondering, how do we know that some new chromatic aberration that we see in the image is actually caused by the tube lens and not by the objective? Well, we deal with that problem by selecting an objective that does all of the optical corrections inside the objective. Some objectives are made where only part of the correction is done in the objective, leaving the tube lens or even the eyepiece to do the rest of the correction. That would not be a good objective to use if you're testing a tube lens. So because the CFI Plan objective does all of that aberration correction in the objective, we know that any new aberrations that we see are introduced by the relay lens and not by the objective. Now, what are we looking for when we test a tube lens? Well, it's the usual stuff you look for when you test a lens. We're looking for sharpness, both in the center and at the edges. We're looking for evidence of field curvature. That is when the image that's projected onto the sensor is not a flat image, but a curved image, where only part of that image will be in focus at any given point. We're also looking for chromatic aberrations. the common and almost unavoidable longitudinal chromatic aberrations that show up in the outer focus areas of your image, as well as the better defined lateral chromatic aberrations that usually appear more often at the edges of the photograph on areas of high contrast, often straight lines. So that's the kind of stuff we're looking for. And because we're using an objective that corrects for all of that, we know that if we see it, it's coming from the tube lens. I set up a little stage to photograph our subject and lit it with two evenly powered speed lights, one from each side. The only reason I used two was to get even lighting across the whole area and not introduce shadows and other issues that could complicate looking at the images. Now, because my method for getting these silicone wafers out of the dense epoxy envelopes they come in, I often will leave behind tiny microscopic pieces of epoxy, either on the front or the back of the chip. And that proved to be a real problem for part of my testing. So to test how flat our field is, we need to have our subject absolutely perpendicular to the axis of our lens. If you think about it, if we're trying to photograph a flat surface to see if the image itself is flat, but if our subject is tilted even a fraction of a degree, then we're going to introduce depth of field issues. The edge that's closer to the camera will be in focus, whereas the rest of the subject isn't. And that became a real problem with my little chips because, first of all, by not mounting them vertically, in other words, lying them on a flat surface, I couldn't guarantee that they were absolutely perpendicular to the camera. So I shot horizontally, which meant that I was placing my subjects manually and then trying to adjust the manual positioning to get them as perpendicular as possible. And we are talking about hundredths of a degree to get that right. And yeah, I gave up on it after a while. So when testing for flatness of field, the information that I got would not be something I would stand behind. So instead, I focused on sharpness and the chromatic aberrations. So let me tell you how the images were collected. My camera and bellows, relay lens and objective were all stationed on a stack shot focusing rail. Using live view on the camera, I would position the camera, lens and objective at the point closest to the camera where a part of the image was in focus. Because my subject wasn't mounted perfectly perpendicular to the camera, the right edge of the image always came into focus first. I had the stack shot set up in manual with a 2 micron step length. So what I'd do is take a photograph, advance the system by 2 microns, let all the vibrations settle down, take another image. And I would go all the way through the image until the last part that was in focus was now blurry. If you had some kind of a high-tech optical test bench, you would only have needed one photograph because that one photograph would have been perfectly perpendicular and everything would have been in focus at the same time, unless you had field curvature, of course, but assuming you didn't. That was nowhere close to what I was able to do manually. So what I needed to do in order to make sense of how the lens is performed, I wanted to choose the sharpest part of the image that I could find. Now, I was limiting myself to the center 10% of the image and to an area around the very periphery because I was comparing center to edge sharpness. But instead of just having one photograph that I could take those image segments from, I needed to have a selection from which to choose the sharpest. There's no point comparing the two lenses, if we take the sharpest point from one of the lenses and compare it to not the sharpest point from the other, we'll get misleading results. So what I wanted to do was collect enough images that I was sure I had a good representation of the best focus conditions that I could find with that lens, and then my samples were taken from those areas. I hope that makes sense. I'm trying to compare the best the Raynox can give me with the best the NiSi can give me for any particular setup. And that's what I did. I collected the images in RAW and I imported them directly into Lightroom. I turned off all the automatic lens corrections. It's very important when you're comparing images side by side like this that you do so at the same zoom factor. So for the purposes of this test, I compared images at 100%. I'll be the first to admit that the data that I was collecting from examining the photographs was extremely subjective. I just examined them carefully and took copious notes. The first configuration I used for both lenses was to shoot with the lens facing in the normal forward direction and at the focal length of the lens. And what I mean by that is the Raynox is a 4.8 diopter lens that has a focal length of 208 millimeters. So for this thing to focus at infinity, it needs to be positioned at 208 millimeters from the sensor. Now, when I switched over to the NiSi, I had to change the extension back to 200 millimeters, which is the focal length of this lens. Then I repeated all of those images with the lenses in reversed position, but otherwise the setup exactly the same. And then in the second half of the experiment, I repeated every test I'd already done, but instead of using the lenses at their focal length, I used them at a short focus length. You don't always have to use the relay lens at its infinity position. Some lenses, when you position them closer to the sensor and effectively reduce their focal length, you're going to reduce the magnification a little bit. But in some lenses, it can result in sharper images. Now, the Raynox is one good example that's been well tested. It is known to be a good performer at 144 millimeters. So for the first half of the experiment, all of those images are with the relay lens focused at infinity. And with the second half of the images, the relay lens is always short focused. I rather arbitrarily chose 144 millimeters to short focus test the NiSi lens. But I think I am going to do some more testing, adjusting that short focus distance to see if I can get improved results. So now, as you know what I was looking for and how we set up the test, let me show you what I found. So in the first set of images, I compared the Raynox at infinity focus with the NiSi at infinity focus, with both lenses positioned in the forward or normal orientation. For the Raynox, the images were acceptably sharp in the center, a tiny bit less sharp at the edges, but hard to notice. And I could see some very subtle chromatic aberrations in the form of purple fringing at the very periphery of the image. So when I looked at the NiSi in forward orientation at its focal length, the center was acceptably sharp, but the peripheral image was not. There was a lot of softening. But what really struck me was there were chromatic aberrations, both longitudinal and lateral, everywhere in the photograph. The next part of the test was to repeat those two tests only with the Raynox and the NiSi turned the other way around, so in reverse. So with the Raynox DCR-150 reversed at its focal length, the edges were slightly sharper than in the forward orientation, and the center was a little bit less sharp. There were quite a lot of chromatic aberrations. This was one of the things that surprised me about this test. I wasn't expecting to see quite that much. The central images with the NiSi reversed were also kind of fuzzy. The edges were a little bit sharper, but not really sharp, and the chromatic aberrations were worse than they were with the lens in forward orientation. So in the second half of the testing, we moved to short focus and repeated everything we just did. So as expected, at short focus, the images were less magnified, about 85% of the magnification we got at their full focal length. But the images for the NiSi at 144 were actually a little bit sharper, both at the center and at the edges. But the chromatic aberrations were as bad. When I reversed the lens, the chromatic aberrations got worse and sharpness was about the same. I couldn't tell a big difference between edges and center, but none of them were that sharp. The Raynox, on the other hand, at short focus, 144 millimeters forward, was significantly and obviously sharper than at 208 millimeters. That was true at the center and at the edges. Though if I had to pick one image, I would say that the center was sharper than the edge by a little bit. There were some lateral chromatic aberrations in the forward orientation of the lens at short focus. They weren't particularly bad, and you had to look for them. However, the biggest surprise and probably the most useful thing that's going to come out of this whole operation was at 144 millimeters with the Raynox reversed. The images were sharper than any other that I collected, edge to edge, and there were no chromatic aberrations. None. And I looked for them. Now, I know that the Raynox performs well at short focus. That's commonly accepted by most macro photographers. But I didn't think the difference was going to be as striking as I found in this testing. So I think we can say we've learned a couple of things from these tests. The first thing is that the Raynox has nothing to worry about right now. It really performs very well as a relay lens. It performs acceptably in all configurations, but it is a stellar performer reversed at short focus. I think we can also say with confidence that the NiSi is not a good relay lens for use with infinity objectives. I would also say that we learned that the claimed apochromatic correction of the NiSi Closeup Lens may be an exaggeration. So to sum it all up, I would say that the Raynox performed a little bit better than I expected, and the NiSi performed a little bit worse than I had hoped. I'm not completely giving up on this lens. I'm going to test it further and see if there are other configurations that may work a little better. But in the meantime, I would say without much hesitation that if you're looking for a good 200mm-ish relay lens to use with your infinity corrected objectives, the Raynox is probably your best bet right now. Well, thanks for watching. I really do appreciate it. I'll be back again in a few days with something else. Until then, take care and be safe. Goodbye.